Hey everybody, welcome to the first exam review. We're going to just go through a bunch of practice problems essentially and keep track of how you're doing. If you're feeling pretty confident, if you're getting most of them right, then you're on track. If you're not doing super well, then figure out which areas you might need to improve on and study up a little bit, and then you can always come back and try it again. All right, let's dive in. All right, let's say I calculate a median household income from a sample of professors at CU Boulder. I have calculated a or an what? Well, I've calculated a descriptive statistic. We know, first of all, that this is a sample because it says a sample in the text. Samples correspond with statistics. If you measure something about a sample, that is a statistic. If you measure something about a population, that's a parameter. Now, it's not a frequency because frequency is just some count or some percentage. Median, of course, is a measure of central tendency, and it's used to describe data. So it's a descriptive statistic. It's not an inferential statistic because that's something that we are inferring about a population from a sample, and we'll get to that more later in the semester when we talk about t-tests and ANOVA and regression and those kinds of things. Let's imagine I give a survey to a sample of students. I ask students to tell me how many cell phones they own. I then calculate a number that I use to guess how many cell phones all students in the population own. This is a or an what? This is going to be an inferential statistic. So we just talked about descriptive statistics. Now we're talking about inferential statistics because you're trying to use a number or data from a sample to infer something about an entire population. And again, we'll be talking a lot more about this as the semester progresses, but if I ever ask you to take a number or data from a sample and use it to guess or to infer something or to make a conclusion about an entire population, that is an inferential statistic. An example of categorical data is blank data. This one's going to be nominal, right? Nominal just means different categories, like eye color or political affiliation or gender or nationality or where you grew up. Meanwhile, quantitative data or interval data or ratio data, those are all things that are going to be involving numbers, numeric responses, which are not inherently categorical. In this distribution, the frequency of 3 is blank. For this one, we're looking at the raw score. That would be whatever variable that you're measuring, anxiety or depression or happiness or whatever it might be. Remember that the participant column, we never, ever, ever calculate anything there. We're not interested in those data at all. They're just placeholders to keep track of which participant is where. So the raw score for whatever independent variable we're looking at here, we see that participant 1 got a 3 and participant 6 also got a 3, scored a 3. So the frequency, which is just the overall count in this case of a raw score of 3, would be 2. There are 2 people who scored a 3, so the frequency is 2. If I have a positively skewed unimodal distribution, then the mean will be greater than the median. The mean will be greater than the median. This graphic nicely sums up where the position of the mean, median, and mode are for different kinds of unimodal distributions. For positively skewed unimodal distributions, the mean gets pulled way out to the right, meaning towards higher numbers, because those outliers far to the right are going to pull the mean in that direction. So in the case of positively skewed unimodal distributions, the mean will be greater than the median. A normal distribution, otherwise known as a normal curve, is symmetrical. A normal distribution is bell-shaped. It's unimodal, doesn't have multiple modes, it just has one mode. It's bell-shaped and it is symmetrical. It can't represent categorical data. Categorical data are just categories, and you can make bar graphs out of them where the bars don't touch. And those categories can be arranged basically any way you want, unless you're talking about ordinal data, which is categorical but can be ordered in some specific way. In this case, though, normal distributions, we are talking about either interval or ratio data, some kind of numeric data that is normally distributed. In this distribution, the deviation for participant 1 is, to find the deviation, remember deviation from what? Deviation from the mean. So first of all, we have to find the mean for all of these raw scores for this sample. So we add up 2 plus 2 plus 1 plus 1 plus 3 plus 3. We're going to get 12. Divide that by the total number of scores, which is 6. 12 divided by 6 is 2. So the mean is 2. When we look at participant 1, their raw score is 2. So if you were to try to find the deviation score, you would take the raw score minus the mean, which in this case is x bar, and it would be 2 minus 2, which gives you 0. The deviation from the mean is 0, because in this case, their score is the mean. The sum of deviations in a sample is blank. The sum of deviations from the mean will always equal 0. It will always equal 0 because wherever the mean is, that's sort of the balancing point of the distribution. So there's going to be equivalent positives to the right above the mean and negatives to the left below the mean when you're talking about deviation scores, and all those negatives and positives will always cancel each other out to make a final sum of deviations to be 0. For a particular variable you measure in a sample, how many standard deviations are there for that variable? Well, there's only going to be one standard deviation, because if you take all the raw scores that participants scored on that particular variable, you're going to use all of those raw scores to calculate the mean and standard deviation. So for any particular numeric variable, there's only one mean and there's only one standard deviation. In this distribution, the sum of squares is blank. The sum of squares is going to be equal to 4. And how I figured that out is, first of all, when you're on your way to calculating a standard deviation, which is where the sum of squares is the numerator of that equation, you're going to look at your raw scores. You're going to find the mean of those raw scores. You'll find the deviations of each of the raw scores from the mean just by subtracting the mean from each of those raw scores. And so we've got, for instance, participant 1, their raw score was 2, the mean is 2, so 2 minus 2 is 0. That deviation is 0. We already calculated that. So you calculate the deviation score for each of the raw scores, and then you got to square all of those deviations. So 0 times 0 is 0, 0 times 0 is 0, negative 1 times negative 1 is 1, negative 1 times negative 1 is 1, 1 times 1 is 1, 1 times 1 is 1. So now we have the squared deviation scores, and the sum of squares is simply the sum of all of those squared deviation scores. So 0 plus 0 plus 1 plus 1 plus 1 plus 1 is 4. That is the sum of squares. I enter a raffle with 100 other people. There are 3 prizes available. You win a prize by having your name drawn out of a hat. Once you win a prize, your name is put back in the hat. Which of the following would use the addition rule? The answer is D. What is the probability of winning the first or the second prize? So remember, when we were talking about the addition rule, the word or is key here. You're trying to figure out what is the probability of one or another thing happening. These other options, what is the probability of winning the second and third prize, that would use the multiplication rule. What is the probability of winning only the first prize? That's just a simple probability. You don't have to add or multiply anything. And what is the probability of winning all three prizes? That would be also the multiplication rule. Imagine you have a normal distribution of a population. The mean for this population is 2. The variance for the population is 4. You have a z-score of 2. The raw score for this z-score is blank. Now this one's a little bit more complicated. So you can see here's the z-score formula or z-score transformation for a population. Well, what we have so far is we have the z-score is 2. We've got the mean, which is mu in this case for a population, of 2. Do we have the standard deviation, which is sigma? No, we don't. We have the variance. How do you get standard deviation from variance? You just take the square root of the variance. So if the variance of the population on whatever variable this is 4, you take the square root, and now you have a standard deviation of 2. All right, so now you got all the pieces except for the x, which is the raw score. Well, if you do some basic algebra, you would multiply both sides by the standard deviation, which is 2. Now the z-score is also 2, so 2 times 2 is 4. And then you would just add the mean to both sides, which is also 2. And then you'd finally find what x equals. And if you do the math, you get 6. The answer here is the raw score that corresponds to a z-score of 2 is 6. Blank percent of the standard normal distribution is below a z-score of 0. Or in fact, any normal distribution that's unimodal and perfectly symmetrical. The answer is 50%. So a z-score of 0 is the mean, right? If you use a z-score transformation and you find a raw score that's equivalent to the mean, well, the mean minus the mean is 0, and 0 divided by any type of standard deviation gives you a z-score of 0. So the mean is always a z-score of 0, and it's right in the middle of the curve. It's right exactly in the middle of that normal distribution. So the amount of data to the left of that, or below a z-score of 0, is 50%. Okay, let's get some practice with mathematical notation. So for this, we have to calculate. Remember, sigma means the sum. This is the sum of the raw scores, x sub I, for participants 2 on the bottom there, through participant 4 up top. So this is saying calculate the sum of all the raw scores from participant 2 to participant 4. So all you have to do is add 4 plus 6 plus 1, which is 11. For the following data, calculate x bar. Well, x bar, of course, means the mean of sample data. So here we've got a sample of 6 participants, their raw scores on some kind of variable. All you have to do to calculate the mean is add the raw scores and divide by the number of scores there are. 4 plus 4 plus 6 plus 1 plus 4 plus 5. Divide that by 6, and you're going to get an answer of 4. X bar equals 4. For this set of data, calculate the variance. Okay, for this one, you would have had to have noticed that we already gave you the deviation scores. So you didn't even have to calculate the mean. In fact, there were no raw scores to begin with. It was just already a deviation score. So you square all the deviations, then you add those squared deviations to give you the sum of squares. If you do that, the sum of squares equals 14, but you're not done yet. To find the variance of a sample, you're going to going to divide by the number of scores minus 1. In this case, n minus 1 would give you 5, because there's 6 scores minus 1 is 5. So 14, the sum of squares, divided by 5, gives you a variance of 2.8. Calculate the standard deviation for this set of data. Well, this is the exact same deviation scores that we just saw, and we already calculated the variance of this set of data. The variance turned out to be 2.8. How do you calculate the standard deviation if you're given the variance? Well, you just take the square root of the variance, and that is the standard deviation. So if you take 2.8 and square root it, then you're going to get an answer of 1.67. Calculate the z-score for participant number 6. In this case, in order to find a z-score, you need 3 pieces of information, right? You need the raw score, which in this case is going to be 5. That corresponds to participant 6. You need the mean, which we already calculated in a previous problem for this set of data, which is 4. And you need the standard deviation. Now, in order to find the standard deviation, of course, you're going to have to figure out the mean first. That's 4. You figure out the deviations of all of these individuals from the mean of 4. Then you square those deviations, add them all up. That's the sum of squares. Sum of squares divided by n minus 1 gives you the variance. Then you square root all of that. That gives you the standard deviation. Okay, so if you've done all the hard work, you should find that the mean was 4, the standard deviation was 1.67, and you are looking for a raw score of 5. So 5 minus 4 gives you 1. 1 divided by the standard deviation of 1.67 gives you a final z-score of 0.60 after you round it. And 0.60 what? 0.60 standard deviations above the mean. Imagine you have a normal distribution of a population variable. The mean for this population variable is 12. The standard deviation is 2. You have a raw score of 13. What proportion of the distribution is above the raw score of 13? In order to figure this out, first you have to convert the raw score into a z-score. So you have 13 minus 12, which is 1, divided by 2, which is 0.5. So now you go to a z-table, or the normal table, or the normal distribution table, or the unit normal table. All of those things mean the same thing in the back of your book. And what you find is that you're looking for the part of the distribution that is above a z-score of 0.5. So that's going to be the small portion, because the z-score of 0.5 is to the right of the middle, and so you're looking for even more to the right than that is going to be the small portion, and you will find that the proportion of the distribution that is above a z-score of 0.5 is 0.3085. If I ask you for a proportion, you give me the entire decimal. If I ask you for a percentage likelihood, then you have to multiply that proportion by 100 to figure out what the percentage is. But in this case, it's just the proportion. Imagine you flip a coin 60 times. What is the probability that 40 or more of those coin flips will be heads? So in order to do this, we can use a normal approximation of basically the standard normal curve, and we can use a z transformation to find a z-score that corresponds to these probabilities. Okay, and so how you do that is with this formula: z equals the raw score that you're interested in minus the mean, which in this case is the number of trials times the probability of success is n times p, divided by the standard deviation. Standard deviation in this case is the square root of the number of trials times probability of success times probability of failure. Probability of success in this case is just getting a heads, which is always going to be 0.5. Probability of failure, which is Q here, is also going to be 0.5. That just means getting a tails. So if you work this out, you've got the probability of 40 or more coin flips being heads out of 60 trials. So you got 40 is our X, that's our raw score of interest. We'll subtract 60 times 0.5, that is 60 trials, times 0.5 is the probability of getting a success, which in this case is heads, divided by the square root of 60 times 0.5 times 0.5. You work out the math and you get a z-score of 2.58. Now, what you need to do again is look up on the normal distribution table. Okay, we're interested in 40 or more of those coin flips being hit. So what is the probability of obtaining a z-score of 2.58 or more? In this case, if you could draw out a little distribution as a mean of 0, because the z-score of 0 is the mean of these distributions. 2.58 is going to be quite far above the mean. 2.58 standard deviations above the mean. So you look in the z table or the normal distribution table, and you're looking for the small portion because we're looking for what's above 2.58 standard deviations, and you find a proportion of 0.0049. That's the proportion of all the data that is above a z-score of 2.58. All right, best of luck on the exam. You can do it. You can do well on this exam. I know you can. Let me know if you have any questions.